Okay students, Assalamu alaikum. तो आज वी आर गोइंग टू स्टार्ट विद मैग्नेटिक सर्किट्स. सो मैग्नेटिक सर्किट्स होते क्या हैं, किस तरह से वर्क करते हैं, वी विल लुक ऑन टू दिस. So firstly we need to understand what are magnetically coupled circuits. So magnetically coupled circuits are the one which are not necessarily be connected physically, but they are connected magnetically. Means ke wires are not contacted physically, but they are contacted magnetically. So if we define magnetically coupled circuit, it means कि when two loops are connected each other magnetically in such a way कि एक सर्किट में अगर करंट चेंज हो रहा है उसकी वजह से दूसरे सर्किट पे इफ़ेक्ट अगर होगा या दूसरे सर्किट के वोल्टेजेस पे कोई इफ़ेक्ट होगा, तो दैट मीन्स दे आर मैग्नेटिकली कपल्ड. फॉर एग्जांपल a transformer, it has usually two coils. So two coils are magnetically coupled in such a way that whenever there is a change in current in the first coil, it causes change in voltage or current in the second coil. So they both are magnetically coupled circuits, right? So for example, in that case, whenever there are two coils which are magnetically coupled, so they causes a mutual inductance phenomena in that. Let's say an example of a transformer. So let us consider a transformer over here. Whenever there is a change in current in this coil, the flux in this coil would be changed, right? So this is basically another coil which whose magnetic flux would be affected by the first one. So whenever there is a change in current I1, it causes change in flux in phi 1, and then it would be causing change in flux in phi 2. So it means that this current is indirectly be affecting the magnetic flux of second coil. So this is phenomena of mutual inductance, which you I guess already have uh, studied somewhere. So let's see over here. So when two coils are in close proximity, it means that magnetic flux in one coil would be affecting the magnetic flux or induced voltage in another coil. So this is basically the phenomena of mutual inductance. And from the Faraday's law of electromagnetic induction, this equation, we know this, that is the rate of change of flux is basically the induced voltage, and rate of change of flux is basically dependent upon the rate of change of current. So we represent this equation by this chain rule of differential equation, that is d phi by di and then di by dt, right? Okay, so this equation has now transformed to LdI by dt. This is the equation, this where L is the self inductance. So we are considering that circuit which I discussed earlier. So here this phi 1 is basically due to this current I1, and this phi 1 would not only be affecting this coil, that is L1, but also this coil L2. So the inductance which occurs in between these two coils is phi 1 2. So here we can see how the total flux in coil 1 is dependent upon the self inductance flux and the mutual inductance flux, which means that this phi 1 is only linked with the coil 1, and this phi 1 2 is linking both the coils. So again we are considering that equation from Faraday's law, that is n1 d phi by 1 d phi 1 by dt, and v2 is due to d phi 1 2 by dt, right? So expanded this equation by using current differential d phi 1 by di1 and di1 by dt. This is the chain rule of differential equation. Similarly for voltage induced in coil 2. So this whole parameter has now converted into M21. Here this M21 is basically the mutual inductance of coil 2 with respect to coil 1, right? So remember this equation, we would be using this equation M21. This is the representation of voltage induced in coil 2 due to current in coil 1. So this is basically the mathematical description of mutual inductance phenomena. Now, in this case, we would see how this mutual inductance is represented in a circuit. So, this mutual inductance is represented by a voltage, dependent voltage source. So, here we can see in figure 1, there are two coils which are magnetically coupled. So, I have marked the dots over here, which are representing the dot convention. Here in coil 1, this current I1 is entering through this dot, and here in coil 2, current I2 is leaving this dot. So how would we represent this mutual inductance? So we would be representing this mutual inductance with the help of this dependent voltage source. So here I have represented this is the voltage induced in coil 1 due to current I2, and this is the voltage induced in coil 2 due to current I1, right? So we will mark the polarity in such a manner. Here we can see this current I1 is entering from the dot terminal. So we can see what would be the polarity on this voltage source. Here we can see we have marked. Similarly, we can see where is the dot. So if the current is entering from the dotted terminal in coil 1, so what would be the voltage induced in coil 2? The polarity would be positive on the upper side and negative from the on the lower side. So the description is written over here, which means that this current I1 is entering through the dotted terminal of L1, and it would definitely try to cause the current out of this dotted terminal L2, right? So which means that this voltage source would be represented as positive on the upper side and negative on the lower side. Similarly, we can see over here that the current I2 is leaving the dotted terminal in L2. So it would try to get the current entered in L1 through this dotted terminal, right? So the equation or sorry, the voltage source representation would be like this. Um, Negative on the top and positive on the bottom. So in simplified way, we can say that current entering in one coil, if it is entering from the dotted end, it would leave another coil by dot end, right? Similarly, if the current in one coil is leaving the dotted end, it would be entering the other coil from the dotted end. So let us see this example. Here we can see these two coils are magnetically coupled by a mutual inductance of J3, right? So we would transform this circuit into an inductance with a voltage source, dependent voltage source. Here we can see this current I1 is entering the dotted terminal. So its impact would be like this. We have already discussed this, that we would mark positive polarity on the upper side and negative polarity on the lower side. Similarly, this I2 is leaving the current, this coil L2. So we would mark positive on the lower side and negative on the upper side. Okay, so we can simply describe this phenomena like here in this circuit. We can see that current I1 is entering from the dot terminal. Since this current I1 is affecting the voltage on the coil 2, so here I have represented this by V2. If the current I1 is entering from the dotted terminal, it means that it would be impacting positively on the secondary coil. So voltage would be positive, just like the one phenomena which you consider, that current, if the current is entering from positive side, so we take the voltage positive, and if the current is entering from the negative terminal, so you take the voltage negative, right? So we are considering the same phenomena. Here we can see if the current I2 is entering from the non-dotted terminal and leaving the dotted terminal, so voltage on the left hand side would be negative, just like this. So here we have considered the same thing. Since current I1 was entering from the dotted terminal, so we have represented this voltage source as positive negative, so overall voltage would be positive. And here this current I2 is leaving the dotted terminal, so this voltage is represented by negative positive, so overall this voltage would be negative. So now we are going to apply KVL on this equation or on this circuit. So this is minus 12 minus J4 I1 plus J5 I1 minus J3 I2. So see, you can see over here, this voltage is negative. Solving this equation, simplify, this would be your equation number 1. And then again apply KVL on loop 2, minus J3 I1 plus J6 I2 plus 12 I2 equals to 0. This would give you equation number 2. Solving these two equations simultaneously or by elimination method, current I1 and I2 would be obtained. So do try it by yourself and check whether your answers are correct or not. So another example we are considering over here. Here these two coils J8 ohms and J6 ohms are magnetically coupled by J2 ohm mutual inductance. 100 volt is being supplied to the circuit. So here we would be representing this coil with a dependent voltage source and also this J8 ohm in series with dependent voltage source. So here we can see that this current I1 is entering from the dotted terminal, and this current I1 is basically entering from the dotted terminal of J6 ohms, and current I2 is leaving the dotted terminal of J8 ohms. So how would we represent this by using dependent voltage source? So here we can see that this current I1, the positive terminal is on the other side. So when we connect this effect with J8 ohm in series with the dependent voltage source, so this polarity positive would be on the right hand side because this dotted terminal is on the upper side, so this polarity would be marked on positive side, right? And here we can see that current I2 is leaving the dotted terminal considering the direction of current. So again, this is marked as positive on the lower side and negative on the upper side, right? So now what would be the current? This current in this branch would be I1 minus I2. So here we can represent this I1 minus I2, and current in this branch would only be I2. So here we have represented I2 with this mutual inductance, right? So apply KVL on this, minus 100 loop 1 minus 100 plus 4 minus J3 I1 plus J6 I1 minus J6 I2 because of this branch being common in both the loops. So J6 I1 minus J6 I2 and minus J2 I2, which was actually the voltage. Similarly in loop 2, this is plus J2 I2 when the direction of current is considering as clockwise, and this is again J6 I2 minus J6 I1. So here we have represented minus J6 I1 plus J6 I2 plus J8 I2 minus of J2 I1, right? And plus of J2 I2 plus 5 I2 equals to 0. Solving these two equations, this is as equation number 2. So you can solve these two equations by using Cramer's rule. So formulate matrix over here. Here we can put the constant values, and there would be the coefficients of I1 and I2. So you can apply directly Cramer's rule. You will get the results delta 1, delta 2 and delta. So you can solve it on your own and check out whether your answers are correct.